All right. So in our last video, we took a look at equilibria, and I actually want to go back to the PhET simulation. So let's pull this up, and I've been just letting it run in the background on my computer. So it's definitely at equilibrium, right? The concentration of B is essentially unchanging. Same with the concentration of A. But now I want to do a new experiment, right? So I'm just going to go ahead and pause this and freeze the molecules. And I'm going to go ahead and add in 100 more A molecules, right? So I'm going to go ahead and just type a 1 in there and hit play. All right, let's see what happens, right? If we add in a bunch more A, what do you think's eventually going to happen over time? Well, we know that B is favored, right, at equilibrium because it's slightly lower in energy. So over time, if we put in more A, it's going to adjust the equilibrium so that we end up creating more and more B, essentially shifting the equilibrium to the right. Conversely, if we go ahead and say, well, what happens if I take B and cut it in half? So I'm just going to trim this down to like 45. What would happen then? Well, if we remove B, then the A's are going to want to replenish the B side. It's kind of weird to think about, but this is one of the cool things with equilibrium, is we can change and push equilibria one direction or another by adding or removing reagents and or products. So let's go ahead and describe that in our notebook. All right, and the name of this is pretty fancy. It's Le Chatelier's principle. And the lab that you have is directly related to Le Chatelier's principle. And Le Chatelier's principle essentially describes what I was just saying. It says that the position of the equilibrium will shift in response to changes made. In the factors of the equilibrium. All right, so let's take a look at some just really basic examples, right? So let's take an example where we've got A and B, kind of like we had in our PhET simulation video. So let's imagine if more A is added. All right, what will happen? Well, then the equilibrium will drive right. Sorry, my handwriting's not great right now. And form more B. Basically in response to adding A, right? So that's a pretty simple situation, which we just saw in that PhET video. In fact, we could see it in real time. All right, but let's take some other examples. All right, rather than thinking about adding more of one, we also took a look at, well, what happens if we remove B? If we remove B, then the equilibrium will shift to replace it. We'll adjust, meaning shift right, to replace loss B. All right, so that's the whole idea with Le Chatelier's principle, is we could either add A, or more of one reagent, which causes the equilibrium to shift that way, or if we remove B, we can also cause it to shift that way. Conversely, what do you think would happen if we added in a bunch of B rather than removing it? Well, if that were the case, then we would shift things that way, right? So we can play around with this. All right, there's another thing I did want to show you too. What happens with endo and exothermic reactions? Well, let's take a situation where A is in equilibrium with B plus heat, right? So in this case, this indicates that the reaction is exothermic. It's a reaction that releases heat. All right, we can actually play around with adding or removing heat as well. So let's imagine this. If heat is added, the equilibrium will shift left and produce more A. All right, conversely, well, what if we remove heat from the reaction? Well, then we would drive the formation of B. So we can actually play around with exothermic and endothermic reactions by adding or removing heat this way, which is kind of clever. All right, I did want to have an important reaction note, or an important note, excuse me, that the equilibrium position depends exclusively on delta G. So if you remember back in my first video, delta G is the difference in energy between the starting materials and products right? So that's delta G. It does not get impacted by EA, or activation energy. By catalysts which lower activation energy. All right, and this is something that a lot of students have problems with, where they're like, well, if we're impacting activation energy, wouldn't that impact the reaction rates for going from one side of the reaction to the other? Well, yes, you are right there. So let's take a look at this image. All right. Whoops, wrong image here. Let me go ahead and delete this. Let's get the other one. All right, so here's the image I wanted to refer to. So we've got an uncatalyzed reaction here, right? Let's imagine we're over on this side. Well, we would have to overcome this barrier without a catalyst, right? And if we did get a catalyst, yes, that barrier would be lower. However, we'd at the same time be lowering the barrier for the reverse reaction, right? So yes, we could lower the activation energy for the reaction going one direction, but at the same time, we'd be lowering the activation energy for the reverse reaction. So that kind of drives home the idea that when we were looking at the PhET simulation, it wasn't the barrier that mattered. Yeah, that might have affected the rate, but the equilibrium position ultimately depended on which was higher or lower in energy. The side that is more stable or lower in energy is going to be more favored. It has nothing to do with the activation energy between the two. All right, I hope that helps, but let me know if you have any questions.